Hello, gentlemen. So today my talk is about the error correcting code for memories. This is outline my today's talk. Firstly, I have the motivation why today I'll talk about the ECC for memory. So I'll review the basic error correcting coding. So this is the tutorial with very introductory level. I do not take you with the very strictly the mathematical way, only some intuition way. And we move to the example, the reported work about the DRAM flash memory, and finally summary. So the question will be, I will receive at the end of this talk. So the first, let's look at the SAM story. This is the memory as a resemble a transmission. So please imagine, so this lady want to some information to her office. Yes. Of course, it's not digital way, but the easiest way. Her information is 011 010 for example. But when the information travels through the air, there will be very severe conditions, wild conditions bad through there. So therefore, her information travel, but for example, receive data is 010 010101. So therefore, the received data is corrupted. That is the situation in transmission. The same thing as occurred in the memory. So as I said, the information is traveled in space by the channel, but information travel in time in memory. So for example, so it's not good for the transmission, but our memory, I'd like to write down the 01010111 blah blah blah. So then I write it down. So then for a while I'll keep it. So the information travel in time. But as you can see, there's some very serious condition. The memory cell is not perfect. It's the same situation analogous to the transmission in the air. So therefore, after a while, we'd like to read out this information. However, maybe some bits are corrupted. So memory and transmission is resemble, therefore the both can be treated in the same way. So let's have this situation in the block diagram. We have a source of the information. We have a target to the information we'd like to convey. So there's a source information will be coding for channel. Channel means, for example, the wireless or the fiber or the cable, such adequate to the channel. So then this information pass through the channel. And then as the target receiver, this information through channel is decoding. Okay? However, as I explained before, in the channel, it is a very severe condition. So therefore, such a severe condition takes as a noise. And as I said, channel is very unstable. Same thing for the memory. For memory, source is correspond to the input data, and the target is correspond to the output data. And the memory circuit, of course, the channel coding is the write circuits, of course. And then we write it down, this information, to the memory cell. In the memory cell, the information travel in time. And after a while later, so we try to read it out. So that is, of course, a read circuit, sense amplifier. However, at this station, same. Memory cell is a very unstable. So the instability affects the memory cells. So therefore, the memory cell is just something affected. Okay? So, to summarize the transmission communication, the information through the channel makes down. Same as the memory information, this example is a multi-bit flash memory. After time goes by, the information is vague. That is a question we'd like to take today. How to do? That is error collecting. So we inserted the error collection coding between the source and channel coding. So the coded, with the code of the error collection, data is again coding for the channel. And then move through the space, and that's the target receiver. Once the channel coding is decoded, and then we inserted again between the channel decoding and the target error collection decoding. So therefore, here, data is recovered. Same thing in the memory. We also insert the error collection coding between input data and write circuit, so that we added something I will talk to you later. And then we write it down in the memory cell. Of course, the information memory cell is very unstable, but after the reading the information, we inserted again the decoder between the read circuit and the data. So the corrupted data will be recovered. Okay, so this is we have to talk today. But why? Why we need such a little bit complex system today? I explain the background. One is this slide shows the power supply roadmap from the idea 203. So they say the supply voltage is reduced step by step. They say the 2010 will be 0.7 volts. And also the LG physical gate length will continuously thinner. That also from the reasonable reliability, the supply voltage will be down. However, this deteriorates the memory cell. Memory is known as hard to follow this trend. Why? Because the memory treats the analog circuit as a signal inside the memory. So therefore, such a reduced supply voltage is good for low power and reliability, but deteriorates the memory signal. So therefore, this little bit of data was this slide shows the horizontal axis the memory capacity, and the vertical axis is the signal charge. The signal charge is decreased. So therefore, the memory going to unstable. To save these trends, but keep the performance, power, and the speed to maintains, we try to take some techniques. In addition, currently, memory is so small, we have had the software by the neutron. The neutron is from the galaxy, but there's a reaction in the air, and the very neutron is showered in the Earth. In the cosmic rays, the produced electron-hole pair is 10 times larger than the alpha particle. That alpha particle is some element in the package, but the neutron is from the galaxy. So this rate is about, in Tokyo, 20 shower per hour per centimeter. Such a kind of neutron is showered. So therefore, there is expectation. The DRAM, of course, it is very three-dimensional. There's a very small drawing area, so it remains stable or something decreasing. But SRAM, it is increased rapidly for the software cross-section. I mean that this is very weak for the software. Also, in the ICC, some reported the neutron software have recognized the serious program for the logic. In the logic, there are such a large electron-hole pairs causes a problem. So such a program shows we need the ECC. Of course, the memory people, we try to keep their trends with many ideas. So this is a rough sketch of the ideas. But now the DRAM is a 1T cells, SRAM is a 60 cell, but their report is other kinds of memory cells. For example, the twin cell is storage with a complementary signal with a high and low is one cell that prohibits instability. However, even such ideas, so the situation is getting worse and worse. Okay, let's back to the error correction. The basic error correcting is very, very simple. Of course, the interactive levels is very simple. If you want to store information 0 or 1 in memory, then but possibility is that error occurs. Then add redundancy bit. The simple way is information 0, add 2 more 0, information 1, add 2 more 1. So then 1 bit error, I mean the 0 turned to 1, can be corrected by simple majority judgment. So I mean the 1 bit error is occurs, but the majority judgment, this is 0. 1 bit occurs, but the majority judgment, that is 1. This is very easy, but this is a principle of the error correcting at all. Okay, so let's see the same way in a block level. I say that complete the same thing. Input data, we'd like to record the 1001. We insert the error correction coding. So in the same way, 1 is 31, 0 is 30. So that converted such a way. So then, through the rewrite circuit, we write down in the memory cell. Of course, there's some disturbance, retention and noise. The memory cell is unstable. Right after that, I read it out. The maybe the stored data is corrupted. This red one is error. However, as the same is the majority judgment occurred in the error correction decodings, we can get the correct data to the output. That is completely the same as the input data. Okay, so this is well known in the communication technology. The communication people says, I'm sure that how many of people from the communication field, that error-free transmission is possible even when the channel is noisy. Just add redundancy to protect information from noise. So here is I put the without the explanation of terminology, but in this lecture I will talk one by one. But roughly take a look at the information, coding, some redundancy through channel and decoding, and you can get the original data. And if this channel capacity as a C, is a transmission ratio K by N is smaller than the capacitor C, the decoding error nearly to the 0. So this means only to say that we can add some redundancy. So this says that we can add the redundancy, any error can be recovered. But however, this is actually connected to the famous Shannon's theorem. So this picture is treated by the IEEE homepage. Please notice down there because the copyright is affected, so that this is the page is from the IEEE homepage. The Shannon theorem is the same. As I said before, if the transmission rate is equal or less than the channel capacity, then there exists a coding technique which enables transmission over the channel with an arbitrarily small frequency of errors. Yes, we can do it, but the drawback. However, if the coding time of overhead to the area becomes infinite as we approach the limit. So therefore, there are many technologies developed about the ECC technology to conquer this limit. Error correcting code, it serves a very long history. So this is classified. Therefore, is a two code. One is a block code I'll explain later, other convolutional codes. And this is also classified as what kind of errors we'd like to trace is also classified. One is a random error, other is a burst error. Burst error is the one line is simultaneously errored. For this classification, there are so many technologies developed, such as Hamming code, BCS code. BCS stands for the 3 persons. Reed-Solomon codes and fire code, and the convolutional Vitavi encoding system. So today, we will try to study some of them. Okay, so what is the benefits of memory? Of course, I talked to what is termed that protects the instability. So therefore, that improves the reliability, including unstableness. That is a well-known example. The virtual access is software rate without ECC. Virtual access is software with ECC. And with the ECC, there's extraordinary improvements can be achieved by ECC. But this is well known, so we are taking a long time. But currently, there is another benefit as discussed in the memory area. Error correction used aggressively for lower voltage, lower power. That is a new trend in the recent days. This is one announcement from the LPWAN memory. They call the super self-refresh. That achieves the lowest self-refresh current. As you know, for the standby mode for the cellular phones, all the power is consumed as the refresh for the dynamic RAM. So they introduced the ECC, so that takes the refresh interval very long. So therefore, they said from only introducing the ECC, they said the power is 1/20th. So it's another story, not the improved reliability, but used aggressively for low power, low voltage. So this kind of study is now running in many of the institutes. This is one example. Okay, the benefit error correction is one is for the improved reliability, and the current is used aggressively for low power and low voltage. Okay, but the issue for electronic memory, that should be fit to the memory configuration. Of course, the error correction itself has a general efficiency, but some technology do not match the memory configuration. We choose the technology that match the memory configuration. Also, it should be compact and strong. And this is a little bit the same with the application memory. So the purpose for each memory that should be matched. So I mean the SRAM, DRAM, and the normal RAM, there's a different purpose. And also the electronic coding is suitable for memory array. I mean the X by Y, M words and N bit architecture of memory. And also when we put the ECC circuit in the concrete memory, so there's many discussion in here. So I will show you later. Okay, so let's study the basic with coding. But I'm wondering this is, I talked today is a very introductory level, so that if you have the course in the university, the error correcting course, so maybe everything you know well, but please be patient such a faithful, but I'll give you a very introductory level. One is the block coding. So if we got the information bit for the some length, so block coding means we divide it into this in a block. The block length is k bit. And block coding means we code it as a unit of this k bit. Okay? So therefore, as I said, we added some redundancy. The resultant bit is n bit. Here, with some terminology, n is the code length, and the original k bit k is the information length, and k by n is the coding rate. And we call that this unit is a word. This is a word. Okay, this is a block coding. And then we look further the block coding. So to make the story simplified, we only think about only the 1 k-bit block coded to the n bit. Okay. So there are many kinds of the block coding, but the very simple way is we prepare some function that creates some information using this k-bit. And we use the original code, the word with the information as it is. And then add the externally bit that are created from the original k bit. That is a check bit. So therefore, the total word length is n as I said. Therefore, the check bit is n minus k. That is the code for the NUK block systematic coding. I use this lecture this simple one. Okay, so we now create some coding, but after that we have many other sequence. So we created one word that is the 8 bit. Okay, the k is from the original data, n minus k is we calculated. So we call the elements in the original ones m1 to mk, and the additional, do you remember that the check bit is p1, p n minus k. And then these coded words is writing to the memory cell. This example is the DRAM cells. But as the time goes by, there's a very unstable, there's an error. So then we read it out from the memory cell. There is not original. That is with the error. So therefore, we call the element for the other word, Rm to Rmk, Rp1 to Rpn minus k. So what to do? Our target is we want to have the original. So therefore, we have the Solong2. Solong2 is calculated from the read error itself, that contains error. That is what we call the syndrome. Syndrome is only contain error information. That is completely independent to the original. That I show later. This is very important with the magic of the coding theory. We can have the syndrome that contains only error info. Therefore, we can calculate to the what is the error. So therefore, we can get the corrected data. That is the system of the error correction. Of course, but the same with the majority judgment. Only but we introduce a syndrome that contains error info that specifies what is the error. Okay, this is the same as your handout. So this is the total outlook of the error collection. Once I repeat, we have the block k-bit unit, and each k-bit is coded to the n-bit length words. And then, so that's the mechanism is we create from the original data to the check bit that's simply added. And this n length words is written to the memory cell, but after that we read it out that with error. So we create a syndrome, and we make the error collection, and finally we can get the result data. Just well done. Okay, so let's actually some example. I only check the first part of this mechanism. To make the story more simple, I assume the additional bit is only one. That is called the simple parity check code. So this is only the parity of the original data. Okay, parity bit, so I assume here the PC. Okay, so therefore this is only one bit that is as a check with parity bit, and the other of them is from the original data. So this parity bit It's simple. That's only the over from the original data that added from it. It's simple. Okay, so let's have the exercise. So this is very simple, but more simple. We assume only the k equal 2, only the first element, so only the m1, m2, and creates only one parity check bit. So you can write down this table very easily. M1, M3 is 0, 0, 0, 1, 1, 0, 1, 1. That's all. The parity check bit, only the switch over, is only the here. Oh yes, the parity bit checks the number 1 is such a guess. Okay, so okay. First of all, so I will show you graphically why we can check the error. So the simple explanation is shown here. So the M1, M2 PC, that's only the 3 elements, so we can take its M1, M2 PC. So therefore this, every bit is plotted here. So this is some intuitional explanation with why we can check the error. So our original datum 0, 0, 0, but one bit is changed. So let's say it's 0, 0, 1. So therefore this is vacant originally. So that we can find that's error. Why? Because that's a system where if the distance, this and this, we can have the 2 change, 1 change, 2 change. And as this here, the 1 change, 2 change. Such a lattice, we have the vacant. So therefore we can check and correct the error. But in this system, the importance is we can find out, oh, this is the error when one finds it. But we cannot correct at all. This is from here, from here, from here, there's any possibility. Of course, there is a distance d and the capacity or the possibility of the correction is to down, but I show you here is only to the why we can check and correct the error bit. Okay, in this 3-2 coding, 1 bit rejection is possible. Okay, so this is the one example. I explained the coding simple parity check. Simple parity checks the added redundancy of the explained over of every bit that can the 3D coding that can 1 rejection possible. Okay, using this simple example, we would like to prepare some mathematical tool. Okay, this is as I'm familiar with the 3-2 coding. So the elements are only 2 and the 1 check bit. This is same to write down such a format, matrix format. That means this M1, M2 PC, please recall this is a coded, so that this is an n coded length words. And here M1, M2, this is original. So, and by the G. So this is a equation for create to the code. So therefore, when we write down this form, we call the G as a generation matrix. this generation matrix is very simple because from the M1, M2 to turn to the M1, M2 PC, PC is exit forward, so therefore the G or M1, okay? So M2 is here, so okay. So the PC is M1 plus M2, so M1 plus M2. So this is a generation matrix. After that, the very complicated things occurs, but this is a very comprehensive example, I think. So then, now we have the generation matrix. So here, so I explain the other simple mathematical words. One is linear. What is a linear? This code is called the linear code. What is the linear code? So as I said, that's 000, 011, 101, 110 is a word. I said this is a word of this coding. So I write it down as a V every word. And here I write a W as every word. So then we have a table to sum up every element. That's the result. And we find out easily that every element is a word of this code. Okay, this is a linear code. So in the textbook way, and code this code is C is called a linear code. It's a V and W are in the C is a word of C. Then the V plus W is a word in C. At this time, this code is a linear code, and therefore, therefore the simple parity check code is a linear code. Okay, so we can guess what is generation matrix and what is a linear code. Okay. Again, so our target is calculate the syndrome. So please be patient. So I will write it down. This is this code equation. Only one equation here. Here is M1 plus M2 PC is 0. As you know, in the infinite theory, the plus and minus is equivalent. Minus plus, plus and minus. So I write down, so in general is that thing. So therefore, this is again write it down with the matrix way. We can rather say this express this question, of course. So M1 V3 and the transverse of the 111 equals 0. In this expression, we can have the sum matrix H. Now, formula is a G, this is H. So we can say using these two matrices, we can write down here the simple one equation for this coding. We can write it down. W was by the transpose with H. This is a parity check matrix we call. It's a very simple parity check matrix. This is H. Okay? Okay, we would like to because again. So we have the word W. And then with the writing, also we have the error. So let's assume the error was as a E, error vector as a E. And with the writing, we have some datum with error. This error down is R. That is also the word. So please assume the carrier only a 2. And the initial word is M1, M2 PC. and then we add some error. So therefore, we can write it down. Our D data is W plus E. That's the element RM1, RM2, RPC. That's each element is M1 plus E1, M2 plus E2, PC plus EC. Okay? So therefore, now we can calculate the syndrome. What's the syndrome? Syndrome defines R by H transpose. R is a lead data, and H is a parity matrix. This is important because what we use is we do not know the original data. What we know is the reader data. That's contain error. So we recover only the error data to the original data. But when in such as this equation, so we can find out the R is written the W plus E. And the important thing is the parity check is WH transpose is 0. That is important. So that is a coding. Coding is defined as W by H transpose 0. Therefore, the syndrome is only dependent to error. So therefore, we can find out what is error by using syndrome. Okay, the syndrome is useful to obtain the error information. Okay, one is, as I explained, is independent W. It's not independent here. Only we can get the error information. So if the S is, in this example 1, when the some error occurs, and the 0 was no error, was many error, such a thing. Okay, so let's say same as your handout to the example with the 3-2 coding. We learned about what is a parity check matrix, what is the syndrome. Okay. So then we move to using another example to study further. So the horizontal virtual parity check code, because I guess the simple parity check code only checks the error, not corrects the error. So therefore, we go further. The parity check code. What is a HV parity check code? Again, so this time we assume that K equals 4. And then, so today's function is HV parity check. So then we add the check bit, we create the code words. So how to do? First, we reassign this first information as this style, M1, M2, and M3, M4. So then we calculate first and the row parity check M1 plus M2, M3 plus MC. And then again, we can calculate the parity check as a vertical column. M1 plus M3, M2, M4, Q1, Q3 get. And finally, we can get, with the parity check code, we calculate the R. So this is the HV parity check. So here, the parity check equations that I told you already. So the P1, M1 plus M2. P2 is M3, 3, M4. Q1 is M1 plus M3. Q2 is M2 plus M4. R is M1, M2, M3, M4. Then we can calculate the generation matrix, parity check matrix and syndrome. Okay, let's go ahead. So therefore, the HP parity check, we assume the 4 information bit change to this M1, M4, and P1s are. So therefore, we added 5 more bits. So therefore, that is a 9 for coding. 4 is the original, and the code length is 9. So it seems that the LV to the rich coding, because we need more about the check width than the original. But however, so we define the word of this here. And then, so as I explained, we write down this expression. So the original to the coding, this is a generation matrix. So generation matrix is here. So we calculate here. That you write down. Well, here. So one is M1, okay, M1, M2, M2, M3, M3, M4, M4. P1 is, of course, M1 plus M2. As you can see, you can get it. And P2 is M3, M4. M3, M4. And Q1 is M1, M3, M1, M3. And Q2 is M2, M4, M2, M4. And the final is all the M1 to M4. All the M1 to M4. That's the generation matrix. So the first part is, as you can see, that is the identity matrix. Of course, we only use it as it is. This is the identity matrix, of course. So, and this part is come from this parity check equation. So this is a transverse. So as I said, this is a transverse parity check equation. This is a parity, generation matrix for the HP parity check code. Then I write to the H. So I write down this equation in this style. I said again, the information is minus equal plus. Okay, from this situation, we write it down from this form. So this is the code words and this H matrix is 0. So therefore, the parity check matrix is for like this. So again, so look at this matrix, we can find, oh, this is the identity matrix, and this is maybe related to the parity check equation. Yes, this is a parity check equation, and this is identity matrix. So we can get G, we can get H, so therefore we can calculate the syndrome. Okay, because that's why we calculate syndrome. I recall your memories for we have the code words right into the memory cell, but the value is very unstable. Therefore, that makes some error. So the reading out data contains the error. So therefore, we can calculate the syndrome. Syndrome is very important because I only use the reading out information only. We do not know the original information, of course. So then, for the R is W plus E, the word transverse H is 0. That is also the definition of the coding. So therefore, we can find out what is the error. Okay, so therefore, if we have this is the last one. The simple parity check is a very simple example, but this is a very complicated. So therefore, win the table was what is error is E is occurs every site has some error can be occurs. With the relationships, the error, the thing that we can have the table. But if once we calculate the table before the execution, so we can find out what is the error. So this is what I said right down here. When I use readout data, we calculate the syndrome. So we look at table from the error between the syndrome, so we can find out what is the error. So then, summation with the original data, we can have the corrected data. So this is what way with HV parity check code. So the next one, so maybe a little bit you are maybe tired. So that I moved to the Hamming code, and again, so I explain these mechanisms. This is Hamming code. Why I moved to the Hamming code? Because HV parity check is very good, but we need many of the check bits. The original bit is only 4, but we need the check bits of the 5. On the other hand, Hamming code is only needed 3 additional check bits. So this is why every people want to use the Hamming code. So here the sequence is the same. From the initial code, we can have the check bit coding. That's the Hamming code check bit coding. So we can add some additional code. So then we make the code words. So the Hamming code is given by this equation. So C1, C2, 3, this is a cyclic change of the first element. And 1, 3, 2, 3, 4, 4, 1, 2. So this is also can define the check bit, such like. So this is identical, and this is based on this equation. Also, we can find the junction matrix. So a junction matrix, that means this is equal G by the original bit. That's a generation matrix. Okay. So the Hamming code as a check bit coding creates 3 bits. The check bit matrix here, and we can calculate the syndrome. Syndrome is such a thing, so we can have only create the error bit. Okay, the sequence is the same here, so we can have the readout data with some error out, so we can calculate the syndrome. And as a table, we can correct it. But here, you can show the table of the error and the syndrome. This is the table. If the E1, E7 correspond to the E1, the error on the M1 bit, E7 is error on the C3 bit. Of course, the check bit also have affected by error. So then, if the first one is errored, syndrome, calculated syndrome is 101. So the blah blah blah. So the E5 has the error, syndrome is 100. That's why we use this syndrome table. We can find out which bit is error. So then we only the summation of the error bit is readout data. We can calculate the corrected data. But one thing using here, so this is a very simple table, so therefore we can calculate it. Yes. But yes, no. As I'll show you again. So before that, this is same as your handout. This is a summation of the Hamming code, as explained. So I'd like to show you how to have the syndrome. This is how to implement the syndrome coding in the memory. So first of all, so we used to have the calculator check bit using this equation. Please remember this equation, M1 through 2, 3, 4, 4, 1, 2. So therefore, we can write down for this simple summation for the M1 to C3. So therefore, we write down from the memory array. This is the coding. So please go again so that we keep this memory for a while. There's some deteriorated. So then we read out. Just a decoding. So this record is first result. This here is 1 to Y7. So read out data as some errors. So please go there or see your handouts. We can identify the error bit by this when the error is syndrome is like here. So therefore, not to show the table, but we can calculate the corrective data by this implementation. This is maybe this is everything the having code. So the remaining thing is how to come back to create your circuits and using this code theorem. Okay. Okay. So we studied with 3 examples. One is the simple parity checks, HV parity checks, and the Hamming code. So every coding has its advantage and also has drawbacks. So when information memory, it's only it's a memory array to the D out IO, the input data. The data we treat is a K bit. So please recall remind the block coding K bit. Then we calculate the check bit. Any coding you want to choose, and then add the element K bit, and choose write down the memory array as the N bit. This is the writing. And the reading, we read out the N bit from the memory cell. So that is the K bit is the data bit. Of course, at this time, both communicated with the error. So we can calculate the syndrome as many ways Hamming or HV parity such thing. So therefore, using the syndrome data with the original data, we can identify the error bit and we recover the corrected data. Yes, so that is the mechanism in ECC memory. Okay, so the next 30 minutes, so we look for the reported works. So one is 1 megabit DRAM with 4-bit ECC. That is was 20 years ago, so that is reported. So this is HV coding. So this is a logical image of the memory cell. The memory cell, this is a memory cell. This is a H parity, V parity, and HV parity. So as I learned before, the memory cell is put in this form. So we calculate the horizontal line, also the vertical line, and then the horizontal vertical line. So that we calculate and the memory in the memory array. So this is the actual implementation of the block diagram. So they calculate the horizontal, vertical track weight. And then after that, so here is they calculate the for kind of the syndrome. Then you can get the correct data. So this is a chip micrograph. So this is a 1 MegaDRAM with maybe the 1984 such a thing. Also, this is also advanced was the same author. That's yes, HB party is very good, but we have the horizontal axis sector, the vertical axis sector. So in some circuit technology, how to compact. So the ECC technology, the basement is mathematically known and very developed. So the circuit designer should how to compact, how to high speed or hidden. That is the role of the circuit designer in the memory. So this is the merged kind of such a thing. So I do not explain the detail, but this is a very compact ECC system. Also, this sector line merged ECC have the overhead is by 1/3 of the basic SP party. So the coding it is very good, but please recall the Shannon theorem. It takes time, it takes overhead. How to reduce the overhead and the time overhead is a very challenge. Also, this is the access time overhead reduced to 1/3. This is the chip overhead down to the 1/3. And this is the effect of the ECC. So in these ages, of course, the problem is software, alpha particle software from the material in the package. So therefore, at the time, they studied many kinds of ECC for the alpha particle. So they said 10 to -6 power the -6 can be reduced by this his developed ECC. And this is another example. This is a cache DRAM. So cache step. So this is so the former one is ECC as merged in the dynamic memory array. But this is ECC as a discrete one. Of course, on the chip, but discrete one using the SRAM array. So this is also the parity, parity generates, and also the readout to the surface parity. And the software rate reduced to the remarkable. And this is 4 chips, the huge chips. So but the ECC is a very large portion of this chip. But in this chip, the 1 megabit ECC chip is established. So this is same most of the 1 megabit with 16-bit. 16-bit, he says a 4-bit ECC is a 4-bit parallel operation. So the 16-bit, he says a 16-bit parallel operation. So in the conquer the Shannon theorem, the parallel calculation is an important tool for how to reduce the overhead with the ECC. So how to parallel calculation is also important. And this is a famous paper from IBM 16 megabit DRAM ECC. So this is a very large code was used was calculate the calculate the syndrome, and then read out the corrective data in the 16 megabit. Also, this write down also the creates the check bit, as I explained, check bit. So the write it down the DRAM. So in his work, is other unique point is he merged with redundancy. So not only the ACC but also the redundancy. So they have very good advance in the yield curve. So that is another development of the ACC. So next is I'd like to explain the cyclic ECC. Before that, maybe the world first DRAM application with a cyclic ECC. This is the work of the 16 level one cell. So there's a very old work that they are trying to the 16 level in one DRAM cell. So they calculate the cyclic code ECC. So cyclic codes are very useful because it can be implemented with a shift register only. So therefore, it will be used to the kind LSI technology. Okay, so this is also the time paragraph for the it's not needed explanation, but the important thing is that they have the 16 level cell bit, so they have the 16-bit reference voltage they read out with the ECC. And also they have studied about the software pattern of the ECC with the 16 level. So they found out the very good software redundancy reduction using this ECC for their experimental dynamic RAM. Okay, back against the cyclic ECC. So what is a cyclic ECC? Cyclic ECC is why cyclic ECC is important because it can be created by the code encoded by only the shift register. So this is before. Therefore, it's very easy to hardware implementation that can achieve the small area and low power. Okay, so the cyclic code is very simple. Of the linearity, sum of any two code, what is the code in also a code linearity. And why we call the cyclic shift of code what is the code that also code what. Cyclic means I miss the good explanation. So for example, x1, x2, x3. So the cyclic x3, x1, x2, that is also the code one. Such a cyclic shift is also the code. It's the cyclic code. So therefore, such a cyclic shift is easily done by the shift register. So therefore, it is easy to treat as hardware implementation. So I cannot go deep in the cyclic code, but here I show you attention was if this code word is here, the v0 to vn minus 1, that's the cyclic code. This is expressed as a polynomial way. So example, the v0, v1x, v2x square, and such a thing was vn x on the power of the n minus 1. So such a system is we can trace the cyclic code. The code is expressed as a polynomial, and then once code is expressed as a polynomial way, forget it to the first expression. And then the generator is also the polynomial. So the first we assume the n minus k is the order of the generator polynomial. So we write it down such a thing. So then, so the original one is order with n. So we could find out the other remaining of the element scarce order is written down the polynomial way. So this is also coding. So if the gx is the degree of the element scale, and if the first factor is x on the power of the n, so this gx generates only adding the k's power that generates the cyclic code. So for example, please be patient on the example. For example, the information first we given as expressed as the polynomial way. Then, so we add this x on the power of r. What r means to the code length is n. So the element scale is r. So we have the code length n's power. So therefore we multiply the x on the power of the r as then divided the gx, and the remainder is shown. So then summing of the remainder. Why summing the remainder? Therefore, this is divided by the gx. Okay, so the divided gx, so remainder is a summation divider. This is completely divided by gx. So that is a code word. So here today, so we already memorize here. So only the information expressed as polynomial and multiply the remains x on the power of r and divided the generation matrix, and remainder is only summing up. Example, coding 011, we like to coding. So the code length is 7. So therefore the code is k is 3. So therefore the element scale is 4. Therefore we write it down the generation matrix is 4th order right here. So then the info is expressed is a polynomial. 011 is only the 1, 1, 0, x plus 1. So then we added this racked order as multiplied. So then x is x on the power of 5 plus x fourth. Therefore, that's divided gx. So it's expressed here. So remainder is this here. So the remainder is x triple plus x. So therefore, as a definition, we're summing up these two. The result is x fifth plus x fourth and x triple plus x. So in the code way 0, 1, 1, the missing x2, so therefore 0, then x1, and missing the x0, so the 0. So the 0, 1, 1, 1, 0, 1 is the code words. So this is a cyclic coding. So this is a code, so therefore we can calculate the syndrome. The syndrome only contains the error. So how to check the cyclic code. So the given data, received data is then divided by gx. The original data is completely divided by gx. So therefore, if the error occurs, we cannot divide. We have the remainder. If we have completely divided, there's no error. So therefore, in such a means, we can check the error is occur or not. Okay. So we also find that the syndrome like here, but okay, so we omitted here. So we can get also the same way with such a but the mathematical way we can calculate the syndrome. Okay, so I will back to the cyclic error again. So before that, so I already discussed the actual other implementation of the memories. The last one is dynamic RAM. This one is a static RAM. The static RAMs are, the program is the current static RAM is a cosmic ray error. That's as I explained, that's the first portion of the slide. This creates a large number of the electron hole pair that damage a bit with not a single bit, but a multi-bit. So therefore, this is a figure of the memory matrix with the red is broken by the software. So in this software is a very serious problem in softwares. So this slide shows the memory has a structure of the very large resistance of the substrate that causes many adjacent errors. So therefore, this report says if once the cosmic ray creates a large portion of the electron hole pair that introduce the bipolar action, so therefore they create many number of errors. So this is the exact operation in SRAM array. So when once the software is occurred, this bipolar action develops the signal of the other node SRAM that causes very serious information broken. So at the time, so therefore this example shows only the how the series of the current situation. So the SRAM cell has a very large resistance in series, and that causes very serious software, and the major data shows high the possibility of the software. So here the figure I want to explain. So therefore yes, we get the error coding tool, but not to depend on such rich error code technology. That's only to show this example is a very primitive way. So if we have the multiple error, these three, so this or these two. So in the memory cells, we have assigned the address to the x direction and the y direction separately. So therefore, we assign not the continuous address sign, but the one by one the address assigned, and only a small simple error code error correction can be saved the error. So I want to explain here. Of course, we have the many good error correction tool, but first things we should think about to make the program very simple. So example, when we do not have the separate address, we use as such a 2-bit error. But when we separate address, this line, we treat this error only a single error. So this is very less area overhead, and saves the timing of the operation. So such actual actual your design, so it's important to such kind of ideas. Okay, so that's why I put this slide here. Okay, so another concern is how to hidden EC suppression. Yes, we understand that ECC is important, needed, but that takes time, takes area overhead. We don't want it. So therefore, how to hidden EC suppression. This is one example for the SRAM. This is an example that in actual access, they do not pass the ECC line. They use only the same way. But when this means some memory blocks do not select it, his hidden ECC can start to work. So this SRAM has his own address counter for ECC. So there is one block with and activates, the ECC is asserted. So then in the background, the ECC suppression is running. But this is possible because when thinking about the system level, was only 1% of the processors activates the SRAM. Otherwise, the SRAM is only waiting. So therefore, when such a kind of hidden ECC has a room to develop. So he says the SRAM, the software rate is 5.4 years per error per megabit. So therefore, this hidden ECC operates only 0.01% of the total operation time. Oh, of course, this is overhead. So the all bit can be checked so many times in the software's interval. So therefore, if one accepts the 0.01% overhead, so they can reduce the software rate by 10 on the power of 8. So that is a good example of how to implement the ECC. And other ECCs, yes, oh, no, before that, this is the same as the last one. The author also simplifies the ECC. So he says this 4-bit is once corrupted, but he assigns a different address to each cell. So therefore, the 4 cell uses only the 1-bit ECC. So therefore, the ECC, so the ECC is area hungry, time hungry. So therefore, the ECC is a very good tool, but we do not depend much on this ECC. So such idea that reduces the software rate by 10 to 5th. So this is his approach. Okay, so once again, I strength today's ECC is a very good tool, but this is has an area and the time overhead. So there are some ideas needed for hidden, as how to simplify the ECC. You can choose itself. And lastly, true example is for the ESQ-PROM. Is a flash memory example that I concluded. So this is also the old work with 64 kilobit CMOS ROM with ECC. So as the purpose of the ECC is the reliability. So the ESCAP ROM has a very thin oxide. So for the hot carrier over tunneling, so they program through the electrode. So therefore, their information is deteriorated by the leakage of the oxide or such a thing. So therefore, they need the ECC. So this is also the 1986 was such a thing. In such a thing, so the ECC has used for this purpose. But currently, the modern European maker also develops the ECC for the flash memory. So this is maybe the last year's ICC. So the 4 gigabit NAND flash. This is a multi-bit flash. Multi-bit means they store data as 2 bit in 1 bit. So there's a very hard for the reliability. So they use the 4-bit PCH. PCH is one of the cyclic codes. So in memory area, so I show you here is the only memory area such rich ECC technology introduced, but never to forget do not ECC too complicated. So ECC should be simple. So, but this work is very good. So if they from the readers the NAND core, they use the syndrome, and they have some special protocols, backlamps. Maybe this is the name of the person that develops this system. So that identifies the position of the error, and also they identify how to correct the error, the chain circuit, so they say. So the highlight of this work is, as I explained, the ECC has overhead, has also the execution time. So they introduced a parallel execution to calculate the backlamps. Also, they introduced such a cyclic code calculation. They also introduced the smart way. So usually the cyclic code shift register is sequentially, but they introduce the unrolled information, so that's the parallelism. Yes, parallelism. And the mechanism introduced, so they reduce the time overhead. And successfully, they say the 4 gigabit NAND flash is established by ECC. But please look here. ECC is very small, but the current itself is very complicated. So as some is not much on my word last, but the current very miniaturized technology can use the advanced ECC technology in a chip. So therefore, we have many kinds of ECC technology, and can be packed in a small area in the modern technology. So therefore, the ECC is next the research area for the future research. So especially I have put some stress again to the low voltage, low power is the main target for the ECC for the next decade. So I conclude today's my talk. So the instability in memory pressure increasing by neutralizing and reducing voltage. So therefore, the ECC would like to introduce that prevents erroneous speech despite any instability. Also, currently the ECC can be used aggressively to achieve low voltage, low power memory. So this is today's my talk. So I added many reference about the actual examples of memory. So I think the major SRAM, DRAM, and was summarized here, I think. But generally, with the textbook is, I think this one, the European Mathematical Society edited a course in error quality code. This is very compact and very good. So I don't think the many Japanese reader here, but in Japanese, famous text-based is the Professor Imai's coding series, good ones for the studies code theory. Okay, thank you very much for your kind attention. Thank you.